Can you guys see the screen as well? Yeah, okay, cool. Well, I've kind of just got the presentation up here, so you can see all the other slides as well. But yeah, look on the first slide. So basically, informed search is today's session. So we're going to look at what informed search is, what it uses, the greedy best first search, the informed search version of that, because there's two versions of it: the uninformed and the informed. And then we're also going to look at the same thing but for pathfinding. So an informed version of pathfinding, which is called A star. And we're going to look through like what A star does, why it's used, and how good is it. And yeah, that's pretty much it for the session. So it's I don't expect it to take too long. So yeah, 20 minutes should be enough, I reckon. Okay, so what's special about informed search? So a key defining feature about informed search that distinguishes it from all the other kinds of search is the fact that it uses problem specific knowledge beyond the definition of the problem itself. So if you can imagine, like we have a pathfinding algorithm. So naturally, with any pathfinding algorithm, what we have is a bunch of nodes, and then between the nodes, we have arcs. When you can reach a different node from one node, you have an arc between that or an edge, and there's a cost associated with traversing that edge. So a pathfinding algorithm just attempts to find the shortest path, aka the path with minimal total cost associated with all the edges it's traversed. And yeah, that's what the algorithm intends to do. And there are two versions of it: uninformed and informed. And the problem itself, the problem definition, would be exactly what I just said before. So the nodes, the edges, and the cost associated with the edges. However, that's not the only information you can derive from a graph. You can also look at Euclidean distance between the nodes, for example, if the graph has been represented to scale. So, for example, if you have like Google Maps, for example, you have all the different like roads connecting out different towns, and you can choose from a selection of different nodes, from a selection of different roads, sorry, to get to different nodes, which we're calling like the towns, let's say. Um, so you can look at the cost or like the length of the road, kind of, but you can also look at the actual straight line distance from one town to another, which would give like an educated guess as towards um which road you should take, so or which direction you should go, and that avoids you from having to traverse every single node and see the actual cost from every single node, making it more efficient. So this extra intel is what generally gives informed search the edge over uninformed search. So generally, if you can have an algorithm with informed search, it's better. However, often additional information isn't available or it's too expensive to derive, which is when we just use uninformed search, which is just it's more like a brute force sort of thing where it just like looks at everything and then finds the best way forward. So the general strategy, so we call that best first search, is used to define which node to expand on the frontier after evaluating a function for each node. So that's what best first search does. So when we're going through any search algorithm, we need to know which node to go on to next on the current node that we're at. And the informed best first search uses a heuristic to determine that. And that's what we're about to come to now. Let's look at heuristics. So a heuristic allows a solution to a problem that's good enough for most practical purposes, even if it's not the most optimal solution. So in terms of like computation, often like we have algorithms for optimization. In fact, that's the whole next like topic that we're covering tomorrow afternoon, optimization. But a heuristic is different. Heuristic is like a viable solution, which might not be the best solution, but for all intents and purposes that we're using it for, it's enough, and therefore it works, it's good. And the benefit you get by not having the optimal solution is that you tend to find a viable solution a lot quicker and with a lot less computational resources being used. And we're not looking for the best solution a lot of the time. A lot of the time, a viable solution will work. Hence why it's called viable, I guess. So the physical Euclidean distance from a node to the destination can be used as a heuristic to estimate cost, and we'll look at this later how it's used in A star. Um, this is called the straight line distance, or in notation, you'll often see it represented as H subscript SLD, straight line distance. Um, and it means that the data slash node need to be accurately placed, as it's not just raw costs we look at. So we need either a accurately drawn out graph, like to scale, or we need the heuristics already in place for us. So often they don't draw the graph to scale, but they have the heuristics already in place for us. So we know the cost to get to a node from another node. And we also know the heuristic to get there as well. But I'm just saying, in the real world, this is how heuristics are often derived. But I assume for our exam question, they'll give us the heuristic values. We won't need to calculate them ourselves. And you can think of a heuristic as like an educated guess for distance from a node to the destination node we're trying to get to. So I said greedy best first search was the algorithm slash method that we use to determine which node to expand in a frontier. And what I mean by a frontier is the set of nodes that we can reach from the current position that we have. For when you go through a pathfinding or a traversal or anything, you visit nodes, and once you visit a node, that counts as like been visited. So from all the visited nodes, the next set of nodes that you could potentially visit, all the candidates that you have to expand, those nodes are called the frontier nodes. And the greedy best first search just decides which node on the frontier you should expand next, the one that you should go to, in all cases. So this is a general approach to informed search, and determines which node to expand, as said, and it's based on an evaluation function. The evaluation function, what it is it just acts as an estimate. So we talked about the cost. The cost is the cost basically of traversing an edge, or traversing arc from one node to the other. So the estimate is just we're trying to get that without having to like actually go and look at the cost itself. The node with the lowest estimated cost is then expanded next. So we're only looking at the heuristic here because we're trusting that the heuristic is going to be a good guess. And why have I called it greedy best first search? It's because it follows the problem solving heuristic, meaning it returns the best solution it can quickly find, which is, you can kind of think of it like a local optimum with gradient descent, without actually returning the overall optimum. So it's not like an uninformed search where it will like look through the entire thing. Here it's only looked and traversed, it hasn't expanded all of the edges as well, all of the nodes is what I'm trying to say necessarily. So it will it might not give you it has no guarantee basically of giving you the optimal. It could, but it might not. It'll depend on the quality of the heuristic used, because it only uses the heuristic to work out which node to expand next. And that is, later on, this greedy best first search is going to be useful, because that's how we decide which nodes to expand in the frontier of an A-star pathfinding algorithm. Okay, so finally, let's go to an example with pathfinding. I'm sure you're all familiar with Dijkstra's algorithm. So that is an uninformed search algorithm. So amongst pathfinding, but they're both search algorithms because you're trying to find the shortest path from a node to a destination node. So Dijkstra's is uninformed. This is because it takes the basic problem definition and attempts to find the shortest distance from each node to the destination node, which means that it has to go through all the nodes of the graph, aka expand all of them, and it does not use any additional information or heuristic. So it only uses the problem definition that it's been given. And let me just check I'm going to open up Discord real quick just to see if there's any questions or anything. Nope, that's all good. All right, cool. A star is an informed search algorithm. It takes the basic problem definition and also a Euclidean distance from each node to the destination node. So remember how before I said Euclidean distance is often a good cost heuristic to use, especially, well, only you can use it when the graph is to scale, such as like maps and things. So A star often, it's not always using Euclidean distance, but often for purposes like Google Maps, etc., it uses the Euclidean distance. And yeah, so I should probably write that down. So it's not always the case it uses Euclidean, but it's just one of the different heuristics that it could use to get a cost estimate for each node. What this means is that it doesn't have to go through all of the nodes of the graph. It can like take a safe bet. So if we're assuming with the map example, if let's say you are trying to find the road to your destination, one road takes you physically closer, straight line distance wise, to your destination. The other road takes you physically further in terms of a straight line distance to your destination from your destination. Well, it's a safer bet to only expand the node with the lower estimated cost. We don't know because we haven't traversed the entire thing. We don't actually know the real cost from each node to the destination. However, with the Euclidean distance, we now have an estimate based on this straight line distance on what the cost will be to the destination. So we are now only going to expand the node which gets us physically closer to our destination and then leave out and not even bother traversing the other one. So yeah, obviously that could lead to a non-optimal path if you like suggest like maybe the one that got you closer has lots of like twists and turns, whereas the one that got you further away would have then been a straight line to the cost, sorry, to the destination. That might be the case. However, it's unlikely. Therefore, we have a safe best bet to just go closer, find everything that goes closer. Yep. So I think Shay's just put a link in the chat. Thanks for that. So that is Dijkstra's versus A star, how it works. So yeah, that's a great example. I assume that it's going to be a good video, and we might watch it in the in this lesson if we have time, because I think we're going to finish very quick. Okay, so now we've looked at A star. Let's look at let's just like look more deeply into the A star algorithm. So how it works, because I've now showed you why one's uninformed, why one's informed, how one works, etc. But these are the exact steps, and we need to know A star for our exams. So I'd recommend just learning the steps of an A star. And thanks to Shay, I think I will actually just, this is going to finish very early, so I'm going to play the A star video, like a run through, which I assume will like run through an example of the A star. So this is a heuristic pathfinding algorithm, blah, 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 as I said in the previous slide. So the strategy involves this evaluation function. So the evaluation function, remember, is what is taken into account when expanding to the next node. So that's what greedy best first search does. So if I quickly go back, it uses the evaluation function to act as a cost estimate, right? So the evaluation function is what's used. The one with the lowest evaluation function is the node that's expanded next in the frontier. So here, the evaluation function is given by this. So f of n is equal to g of n plus h of n, where g of n is the cost to reach each node, and h of n is the heuristic from node n to the goal node. So we at this point we know the cost to get to a certain node, and we also know all the estimates from getting to the destination node from every single node. So when you add these together, you get f of n, and that is the final like value that is used to determine which one's going to be expanded. So you can kind of think of it like Dijkstra's actually. You can think of it like a Dijkstra's if you're familiar with the Dijkstra's algorithm, which we learned in like DSA. So you can think of it like a Dijkstra's, but instead of using the real costs, it's just using a different number, which incorporates a heuristic as well. But once you have the heuristic and you have that like f of n written down for all of them, you can kind of treat it as a black box and just apply Dijkstra's. But that's kind of what's going on under the hood. So the steps. So it follows a pretty simple three-step iterative algorithm actually. So the frontier refers to the set of nodes that are being considered for explanation, as I said. So step one, we need to expand the shallowest node in the frontier with the smallest evaluation function, where the evaluation function, remember, being the cost plus the estimated cost. So the smallest value of that is what is called the shallowest node. And then step two, if a node is in the list of visited nodes, do not add it to the frontier. So if you've already visited it, it's a bit of a waste to visit it again. So you do not want to add it. Even if that's got the lowest cost, you don't add that because you've already been there. And you just keep doing this, keep adding these nodes to your frontier, or sorry, yeah, keep expanding them until you reach the goal node, which is in essence all Dijkstra's does as well, but just with the actual cost. Okay. And then obviously when you get the final output value, which is the length of the path from the node you started off with to the destination node, that length is just the real cost. It's the sum of the real costs. You do not include the heuristics in that final cost. It doesn't make sense because you kind of have like a double for some like a double cost sort of thing because you only want to include the real costs. So once you have chosen a path using the heuristic, you then discard the heuristic or you don't include that in your final measurement, which is quite crucial. When you have like questions to do with this, you have to make sure you discard slash disclude all of the heuristic values in your final path. The final path should only be the summation of the real costs in the path that you've chosen. I hope that all makes sense. I haven't actually seen any questions in the chat, but please feel free if you have any question whatsoever about anything I've covered so far, just pop it into the chat at any point. You don't need to like wait for me to say any questions. And with that, we get to our final slide, the performance of A star. So basically, there are four aspects we're going to look at, which is completeness, optimality, time complexity, and space complexity. So completeness. What do I mean by completeness? So completeness just means that a solution will always be found if a solution exists. So this means that A star will always give a path provided the graph is fully connected. So if you have a fully connected graph, or even like a graph that, there is a path that exists to get to the destination, you will get a result. It won't like stop and give you an error. So that's good. That is what we need from algorithms, that we want to be reliable. If their solution exists, we want a solution. So that includes its reliability, which is why A star is so commonly used. So yeah, it is complete if the heuristic is also consistent. So that is a minor caveat to remember. So if the heuristic is inconsistent, so if you have a bad heuristic or like an inconsistent one, it could just lead you in circles. But I guess you'd eventually reach a solution, but it would not be like a good solution at all. So a lot of what you'll see on this slide with the performance of A star is fully dependent on the quality of the heuristic that you've used. Because the evaluation function that we're using to best for search expand the frontier nodes is a sum of the actual cost to that node plus a heuristic from that node to the destination. If that heuristic is unreliable or like wrong most of the times, then you're going to end up going in like the wrong direction and get a very bad kind of path to get there. So the heuristic quality and the consistency is highly important, and A star is very sensitive to the heuristic. So I can't stress how important the heuristics quality is to A star. It's like the make or break of like will you get a good answer or not. Okay, so now we have a heuristic. It said okay. So I said before heuristic is consistent. So what do I mean by consistent? There's actually a formal definition, which is consistent. It's not like it's just all like yeah, it all works. It's all the same kind of thing. So what do I mean when a heuristic is consistent or monotone is the other word? So make sure you remember this. I'm pretty sure that they could ask about consistency of heuristics in the exam. So if the estimate is always less than or equal to the estimated distance from any neighboring node to the goal node, plus the cost of reaching that neighbor node from the current node, then the heuristic should be consistent. So basically, what that means is the the cost of getting from one node n to another node n apostrophe or n prime n dash, whatever you want to call it, Um, so basically, you have to make sure that the cost to get there is less than the cost based on the heuristic plus the real cost to get to the other node. Does that make sense? Do you understand what I mean by a consistent heuristic? Otherwise you'd end up with like heuristics that are bigger than, or like heuristics that are like, pointing you in the wrong direction or don't make any sense because they would have inconsistencies. Do you get from this definition here what I mean by consistency? I don't know if I've explained that too well, but yeah, no one seems to be asking anything. So I'm gonna move on to time complexity. So time complexity. What do I mean by the time complex? Well, we all know what time complexity is realistically. So the time complexity of A star is O of B to the power of epsilon D. And what this means is that's like the formal definition. Thanks, man. Okay, so that's the formal definition, and where D is the depth of the solution and B is the branching factor. So the relative error of a heuristic is now also, this is a formula that you can remember. I don't think it's given to us, so probably remember this formula. The epsilon is h star minus h divided by h star, where h star is the actual cost from the root node to the goal node. So do you understand what everything kind of represents? So B is a arbitrary branching factor. That's like just given. Um, and D is like the depth. So how far are you going in the solution? And then I've just shown you how to work out what the value of epsilon is based on like the cost or the actual cost. So H star is the actual cost, and H would be the no H star would be the H star is the actual cost. H would be the estimated. Okay, and finally, space complexity. Space complexity of A star is O of B to the D with exactly the same meanings as the one above. Same like the variables mean the same thing basically. As all expanded nodes and all nodes in the frontier are kept in memory. That's why it's B to the D. Because B would be the branches and D would be the depth, right? So you want to do like, it's going to be the branch multiplied by itself D number of times. And this can be an issue, especially for large scale problems, as A star um, keeps all generated nodes in the memory. So if you have a large like problem space, A star can be problematic because of the space complexity. Normally, time complexity can be managed. Normally, we're talking about like time complexity as being like a limiting factor. We have to, make sure it's in polytime, etc., and whatnot. But oftentimes, in practicality, space complexity does actually turn out to be a problem for the A star algorithm. So that is actually everything we need to know about informed search. It included heuristics, the greedy best first search, and A star algorithm, and then the performance of it. So now, as we're still like running quite early. I have a video here that Shay has also put into the chat. So I'm just gonna put that onto the screen. I'm gonna hope that you guys can see my screen as well. So can you see the screen? More importantly, are you hearing anything? Oh, okay, to be fair, I'm not even hearing anything. Perhaps this is a video without sound. All right, cool. That's fine. If you understand how A star works or you've seen this video, yeah, it's fine. This is what I'm gonna just do to like spend the last couple minutes. But yeah, I assume if you want to see this video, stick around. There's nothing else in the slides though, so yeah. Yo, you're not gonna miss any content if you leave now. Shay, is there supposed to be sound in this video? Okay, cool. Alright, that's fine. I see. Okay. So as you saw, with the A star one, right? I'm just gonna show that again. So Dijkstra's, if you just look at Dijkstra's again, uninformed search, it's traversing everything. It's kind of going in a circular way. So it's got a radius, it's going everything almost equally, trying to find the destination, and it's taking quite a lot of time because of the amount of like paths it has to go, has to like do. So it took them a total of what, 21 seconds or something. I think they put, yeah, 2104. Whereas if you look at how A star does it, um, it will use the heuristic, aka the Euclidean distance. So, oh, I just wanted to pause it right before. So here you can see that it's barely explored anything on this side at all. It's almost traversed none of the streets on this side because it's in the opposite direction. The heuristic to get to this side would be further. So it's thinking there's no point going in this direction because, well, the heuristic is further. So because of that Euclidean straight line heuristic, it's now more incentivized to expand nodes in this direction, which is what it's doing, and it's got to the destination a lot faster. As you can see, even on the sides, nothing much has been explored. And there we go. So it reached it in a total of 2 seconds, right? So you can compare. It's almost 10 times worse Dijkstra for this specific example. So yeah, that is pretty much it. So I'm pretty sure it's just gonna show us this same thing for like a bunch of other cities now. But yeah, that's pretty much how A star works. That's why informed search is often better than um, other forms of search, like uninformed search. And yeah, that's pretty much it from what I had today. That's been a um, exhaustive list of all topics involved with informed search. Anyone has any questions before I finish off? Feel free to put it in the chat. No? Okay, well, I'll end the recording here then. And thanks for watching, and see you. Bye.